Welcome to The Explainer. Today we're going to pull back the curtain and decode the incredible journey that happens inside your computer every single time you do something as simple as click your mouse.
You know, it feels instantaneous, right? Almost like magic. But it's not magic at all. It's actually a precise, lightning-fast journey of information, a chain reaction of perfectly orchestrated steps. So let's follow that journey together, from start to finish.
But before we can actually follow that click, we got to set the stage a little bit. The word computer covers a whole lot of ground. So what are we really talking about here?
So on one hand, you've got your general-purpose computers, right? Like the laptop or desktop you might be watching this on. They're the jack of all trades. You can write an email, play a game, or edit a video. But then you have special-purpose computers, which are built to do one thing and do it perfectly. Think about the system in an ATM or even your digital watch. And here's the amazing part. Whether it's a multitasking powerhouse or a single-minded specialist, the fundamental process we're about to explore is exactly the same. That's our starting point.
Okay, let's get into it. The journey starts with you. You've decided to open a file, you move your cursor over the icon, and you press the button. Click.
The second you click, your mouse, which is an input device, sends a signal. That signal zips over to the computer's memory, where it's identified as an instruction. In this case, hey, open this file. That instruction then gets lined up and sent off to the brain of the whole operation, the central processing unit, or the CPU. So, our little instruction has arrived at the CPU. This is where the magic really happens. This is the moment your simple click gets translated into a real command that the computer can actually understand and, do something with. So let's look inside the brain.
The CPU is kind of like a two-person team. First up, you've got the control unit. Think of it as the conductor of an orchestra. It's not playing any instruments itself, but it reads the sheet music, your instruction, and tells all the other parts of the computer what to do and when. Its partner is the arithmetic logic unit, or ALU. This is the calculator. This is the part that handles all the math and all the logical questions like, is this number bigger than that one?
And what's truly incredible is that this team works in a constant repeating loop. It's called the fetch, decode, execute cycle. First, the control unit fetches the instruction from memory. Next, it decodes that instruction to figure out what needs to be done. And finally, it sends that command to the right place, usually the ALU, to execute the operation. This cycle is the literal heartbeat of your computer, and it repeats millions, sometimes billions of times every single second.
But hold on a second, how does a calculator that's made out of silicon understand an instruction like open a file? How can it even do math? It doesn't think in words or even numbers like we do. Well, it all comes down to the computer's native language, binary. Everything, and I mean everything. Every instruction, every number, every single letter gets broken down into a series of ones and zeros. These digits are super simple. They just represent an electrical state of on or off. Even our everyday numbers, like the ones you see here, have their own unique binary code. It's the only language the hardware really gets. And this whole system gets even more clever. Think about subtraction. You'd assume a computer needs a totally separate function just for a minus, right? Well, nope, it uses a brilliant trick called 2's complement. This is basically a method of writing negative numbers in binary that turns every single subtraction problem into a simple addition problem for the ALU. It's an incredibly elegant solution that keeps the hardware design way simpler and much, much faster.
Okay, so we have the input, we have the brain, and we've got the memory, but they're all separate parts. How on earth do they all communicate with each other at these insane speeds?
They communicate using a set of electrical pathways called a bus. You can think of the bus as the computer's internal information highway, or maybe its central nervous system. It's the whole infrastructure that connects all the major components, and it allows data and control signals to just flow between them.
But this highway isn't just one big road. It's actually made of 3 specialized lanes, all working together. The address bus is like a GPS. It tells everyone where the data needs to go. The data bus is the cargo truck, carrying the actual ones and zeros. And the control bus? That's the traffic signal system, sending out signals like read this or write that to make sure everything happens in exactly the right order.
So let's just recap that whole journey. Your click was the input. The CPU doing its whole fetch, decode, execute dance was the processing. The information being held in memory was storage, and when that file finally opens on your screen, that's the output. You've just watched the fundamental cycle that powers our entire digital world. From a physical motion to a digital result on a screen, this whole elegant cascade of events happens pretty much instantaneously. It's an incredible feat of engineering that just keeps getting faster and more efficient every single year. It really makes you wonder, as we keep building on this amazing foundation, what will the future speed of thought even look like?